Hello, everyone. In the last class, we just introduced some basic knowledge related to scheduling, and we learned the meaning of scheduling. The scheduler as a core part of the operating system. It is responsible for scheduling, and it needs to select a process from all processes in the ready state at a certain time. And we just classify the processes into two types. And you can see for the compute bound processes, they just spend most of their time on computing, and the typical compute bound processes are is the compiler, the process of a compiler. And for the I/O bound processes, they just spend most of their time on waiting for I/O. For example, the Word is kind of I/O bound because it needs to accept, it needs to receive the tapped characters from the users. And this just takes a lot. This just takes a lot of time to get those input. So you have to understand the two categories in the in the computer. There are roughly two kinds of processes, and for the scheduling, different scheduling algorithms, maybe they have different rules on select different characters of to select the different types of the processes. So we also know how to when to schedule, when to call the scheduler, when to run the scheduler to select a process to run next. And basically, there are four cases to run a scheduler. The first case is about the created new process, which is definitely created by its parent process. So after this new created process gets ready in the system, uh, the scheduler should decide the next one to get CPU is the parent process or the child process. So this is the first case to call the scheduler. In this case, you can see there is a new process which turns into the ready state from the new state. Uh, and for the next two cases, in these two cases, you can see no matter a process exists or a process blocks. It means the CPU is free again, is available because the last process in CPU just leaves CPU. So now the CPU is available. So for these two cases, the scheduler will be launched too. And for the last case, it's about the interrupt, the I/O interrupt or the clock interrupt. If there is any interrupt happening in the system, and CPU needs to handle that interrupt, right? And maybe it needs to the way to handle that interrupt is to call the scheduler to select a new process to get CPU. So these are basically four possible cases to call the scheduler to select a ready process to get to get into the CPU to run its new instructions. Also, we just learned that the scheduling algorithms can be divided into non-preemptive and preemptive ones. So you need to understand the difference between the non-preemptive and preemptive scheduling algorithms. The for the non if we adopt non-preemptive scheduling algorithms, it means the process the process just leaves the CPU only when it doesn't need CPU at that moment. For example, if it needs to wait for something to happen, it needs to block itself, or if just exit, if it just finished all its job and it needs to exit, then it can release the CPU too. So, uh, with the non-preemptive algorithms, the process in the CPU can run as long as it needs. But for the preemptive scheduling algorithms, the scheduler can decide to use to allow a certain process replace the current process in the CPU, no matter this current process wants to stay or leave. So even though the current process in CPU wants to run more instructions, uh, the preemptive algorithms can just push them out of the CPU, can force them to get out of the CPU. So this is the basic difference between the non-preemptive algorithms and preemptive scheduling algorithms. And we just talked about the we know that there are roughly three kinds of systems we need to take account of. For the batch systems, it means the jobs, the batches of jobs running in batch systems, they usually need less, require less interactions. So basically, we just adopt non-preemptive algorithms or preemptive algorithms with long time periods for each process. So we can reduce the process switches and improve the performance because usually the jobs running on batch systems, they are compute bound processes. So we should know that non-preemptive algorithms are more suitable for batch systems, while the preemptive algorithms are more suitable for interactive systems. Because in for this kind of interactive system, the users care about the response time. After the users submit any request to the operating system, they will expect that they'll get the response in a very short time. So you need to allow the new request to get the CPU to run some instructions and respond to the users. So usually we just adopt preemptive scheduling algorithms for interactive systems because the response time is very important for this kind of systems. And for the real-time systems, usually we don't need to adopt preemptive algorithms because usually the processes running on real-time systems, they just do their finish their job very quickly, and they're gonna block themselves without others' interruptions. And if or furthermore, or if we adopt preemptive algorithms, you might force a process out of the CPU while this process needs to get the result in before the deadline, right? So if you adopt preemptive algorithms, you might force the process not to meet the deadline, and meeting the deadlines is very important for the tasks running on the real-time systems. So basically, based on the two kinds of algorithms, we should know which kind of algorithms is suitable for which environment or which systems. Also, we just introduce something about the goals. Actually, the goals means different criterion to evaluate if this scheduling algorithm is better than the others. So for all systems, we should ensure that the fairness, the policy enforcement, and the balance among kinds of computers, including computing resources as like CPU and the kinds of I/O resources. So these are the three basic goals to be achieved for all systems. While if we just think of batch systems, uh, the most two important indexes are throughput and the turnaround time. Uh, so we just need to focus on this turnaround time. As you see, I have to emphasize the concept of this turnaround time because we need to calculate the different turnaround time for different algorithms in this class. So here you need to pay more attention on this definition. Turnaround time, it means the average time of a batch of jobs from the moment that the job is submitted until the moment it is completed. Actually, the average turnaround time is the average completed. Actually, the average turnaround time is the average value of multiple different jobs. Each job will has a corresponding turnaround time, and that time means the period from the moment that this job is submitted until the moment it is completed. So here we just focus on this concept, this turnaround time, and you should understand that turnaround time should be shorter. The shorter the turnaround time is, the better the algorithm is. So if we apply different multiple scheduling algorithms on exactly the same batch of jobs, then the algorithm with shorter turnaround time will be the better one. Okay, and if you think about throughput, it's okay, but usually you can see if we can get shorter turnaround time, usually we can get higher throughput. So basically, we just focus on this second criterion. It's enough. So this is for batch systems, and for interactive systems, we just mentioned that the response time is the key criterion for these interactive systems, because the users need to get their response in a very short time. But you can see, because during the process's life cycle, the users might type a lot of commands, and each command has its own response time, and it's very hard for us to simulate this process and to calculate the exact response time. So on the course, during the application of the algorithms on a certain scheduling problem, we just focus on the turnaround time of the processes for interactive systems. okay, because it's easy to calculate the turnaround time, but it's not so easy to calculate the multiple response time for multiple requests during the during uh, a single process's life cycle. So this is about the interactive systems. We know that the response time is the most important criterion, but you also need to understand that when we learn the theory, when we learn the algorithms, we have to use the turnaround time to evaluate the different algorithms for this kind of systems. And for the real-time systems, of course, it's very important for the algorithms to meet all or at least most deadlines. But we don't introduce any concrete specific algorithms for real-time system. But you need to understand the way to calculate if this real-time system is schedulable, and we'll talk it in after we introduced the specific algorithms for both batch systems and interactive systems. So after we learned all this basic, after we already understand all this basic knowledges relevant to the scheduling, we can dive into the details of a lot of or multiple scheduling algorithms. You need to know there are compute bound and I/O bound processes. You need to understand when to call the scheduler to select a ready process. You need to understand there are two different types of algorithms, non-preemptive and preemptive. You also need to understand that different systems, different environments, they have different requirements, have different criterion or criteria on the algorithms evaluation. But basically for this course, we just focus on one criterion. It's called turnaround time. You need to learn how to calculate the average turnaround time for a batch of jobs. So in the last class, at the end of the last class, we just introduced you the simplest algorithm, which is called first come, first served. The abbreviation for this algorithm is FCFS. It's very simple. It's just need to assign the CPU according to the order that the jobs arrived at the system. It means the first job the job arrives first, then the job arrives first can get CPU first, and then the next. So it's very simple, but it has a big disadvantage because it's not friendly to I/O bound processes. So here you need to understand what's I/O bound processes. For this kind of processes, they just spend a lot of time, spend most of time on I/O operations. It means usually they just need a very short time to run a few instructions in CPU, and then they'll just need a lot of time to issue some commands relevant to the I/O operations. So for this kind of processes, if you just choose FCFS algorithm to schedule for them, you'll see each one will have to each I/O bound process. It has to wait for a long time to get just a tiny a very short time to run to run only a few instructions in CPU, and then after this process finishes its I/O operations, because there are multiple processes in in the system during the same period, right? So after this process finishes its I/O operations for once for one time, then before it moves on to the second I/O operation or the next I/O operation, it has to stay in the queue, in the waiting queue for a long time to get only, maybe they just need a few milliseconds, and then maybe they wait for over 10 seconds or even more or even longer to get just to get only a few milliseconds of CPU time, and this is so how to say, low efficient for this kind of I/O bound processes, because they don't need a lot of CPU time, they just need a very short time. And if we allow this I/O bound process to preempted the process, the current process in CPU, it it doesn't need to wait for over maybe 10 seconds to get only 10 milliseconds of CPU time. So in this way, it can finish its all the I/O jobs in a comparatively short time. Because if we allow the I/O bound processes to take the CPU from the current process in CPU, we just shorten the waiting time of this I/O bound processes a lot, and this saved them a lot of time, because they don't need a long time to run a lot of instructions. It's okay for those processes which are interrupted by the I/O bound processes, because they just need a very short time. So you can see FCFS, this algorithm, they are not so friendly to I/O bound processes, and usually maybe some users they just cares about the turnaround time or the response time of these I/O bound processes a lot. So usually we don't simply just adopt this FCFS. Sometimes we can modify it or combine this FCFS with other algorithms to put the modified algorithm in the real system. So the second scheduling algorithm you need to master, you need to grasp is the shortest job first. And the basic idea for this algorithm is very simple too, because you just need to choose the shortest job every time when the scheduler is called. It just picks the shortest job in the waiting queue. So of course you need to know the estimated execution time for each job. Uh, Usually for the tasks running on the batch system, this the evaluated or the estimated execution time can be can be can be aware of or can be known in advance, cause so we can adopt this shortest job first. But sometimes you can see in some in some systems, especially for the interactive systems, it's very hard to see. It's very hard to evaluate, to estimate the possible execution time for a process. So SJF is simple too, but it's sometimes it's hard to be put into the real system because they need some parameters. They need at least estimate, not exact execution time. At least you need to provide the estimated execution time. But if you have such parameters, if you have such information about the execution time, you can choose SJF. You can choose shortest job first to get the optimal performance for the batch systems. But you have to notice that the SJF is optimal algorithm for batch systems only when all the jobs are available simultaneously. That means all the jobs arrive at the system almost the same time. Then you can get the shortest turnaround time with this SJF algorithm. Only for this case, the SJF is the optimal. Only when all the jobs are available, arrive at the system at exactly the same time. Only in this situation, SJF is optimal. But why it can be the optimal solution? You can see you can prove it based on some theory. But here we just suppose a simple. We just give you a simple example. So we suppose there are 4 jobs, and these 4 jobs with different execution times, A, B, C, and D. So if we suppose the first job finish this A, B, C, D, they just get into the CPU in this order. So job A is finish it first, and then B, and then C, and then D. So you can see the turnaround time for the first job is A, and the second time it just finish its job at time A plus B. The second job uh, running in the batch system will finish at time A plus B, right? We just suppose these 4 jobs, they arrive at the system simultaneously. So for them, the starting time of the turnaround time is 0, and the completion time for the first job is time A, but the completion time for the second job, it should be A plus B, right? Because the second job needs to wait for the first job finish get out of exit, and then the second job can get into the CPU to run some instructions, and it needs time of B to finish its job, and then C, and then D. So you can see the average turnaround time should be calculated based on this expression. And in this expression, you can see that the value of A is will have the biggest effects on onto the mean turnaround time, right? So the first job, the shorter the first job is, the shorter the mean turnaround time. So we just need to sort the 4 jobs with their based on their execution times. A is the shortest one, D is the longest one, and then we can get the shortest turnaround time, which is the minimum value of the turnaround time, and which means this SJF for these 4 jobs arrived at systems simultaneously, it's is optimal. This solution is optimal. So this just some theoretical analysis. Uh, After we learn the basic idea of the FCFS and SJF, we can illustrate you this example by applying these two algorithms onto this specific scheduling problem. So here we just provide 4 jobs arrived at almost the same time. That means all the jobs, if you want to calculate their turnaround times, you need to use the completion time to subtract the 0 because they just arrived at almost the same time. And we suppose that A needs 10 units to finish its job, B needs 8, C needs 6, and D needs 4 minutes. So here, the average turnaround time with FCFS is 20 minutes. You can calculate it, and we'll show you how to get this number. So when we apply some algorithms to solve a scheduling problem, I strongly suggest you to draw a time axis for CPU, just like this, just like we as showing on the slide. So we just need to put the 4 jobs onto this time axis according to different algorithms. Because with different algorithms, the execution orders, the execution order for this same 4 jobs maybe it's different. So for FCFS, it means the execution order should be A first, then B, then C, then D, because in FCFS, the jobs are executed in the order they arrive at the system. Although we suppose the 4 jobs arrive at almost the same time, but exactly speaking, you can see there must be an order. They can't just arrive at the system at exactly the same moment. There must be some jobs are very shorter than how to say some jobs will arrive at the system just a little tiny earlier than the others, right? There must be a certain order among these 4 jobs. So we suppose that the order is A, B, C, D. So for FCFS, the execution order should be A, B, C, D too. So A needs 10 minutes to finish its job. It means at time 10, A just exits. And at this time, B can get in the CPU and runs for 8 minutes, right? Because job B needs 8 minutes to finish its job. So when does B exit the CPU? You can follow these steps to get the time when B exits. It should be 18, right? 10 plus 8. So at time 18, job B just exits the CPU. So at this point, you can see if we recall the 4 cases to call the scheduler. At this time, B just a process exits. It's relevant to the second case. B exits, so it means CPU is available at this moment. The scheduler will choose the next one. The next one should be C because according to the order they arrived at the system, C must be the next one to get CPU. And when you can see the time when C exits should be 18 plus 6, right? It should be 24. So, and so on, we can get the D will exit CPU at 28. So if you just draw a simple line as the time axis for CPU, you can get the you can get the completion times and starting time very clearly based on this axis. So if you need to calculate the average turnaround time, it should be calculated based on this expression. Uh, the first one, A, B, C, D, is the execution order, and the turnaround time for A should be the completion time 10 minus 0, because we just suppose they all arrived at time 0. And turnaround time for A is 10, and turnaround time for B is 18, right? 18 minus 1. And turnaround time for C is 24. Turnaround time for D is 28. So you can get the average value should be 20 minutes. So here is the way how we apply the different, how we apply a specific algorithm onto a given scheduling problem. In the quiz and in the for the assignments, you need to do the similar things based on their slide. You just draw some axes and put the different jobs or different processes onto the CPU axis, and you get their completion times and calculate their turnaround time respectively and get the average value. That's the final answer. And you need to put on the note on the exercise book or on the sheet. So this is for the FCFS, and if we adopt SJF, if we adopt this algorithm to schedule for the same 4 jobs, then we'll get a different result on the turnaround time. So let's just follow the steps to. First, we need to at the at the very beginning, at time 0, these 4 jobs you can use you can take them arrive at the system simultaneously. So at the very beginning, you can choose, the scheduler can choose a process from A, B, C, and D. So which one will be chosen according to the basic idea of shortest job first? It must be job D, right? Right, job D. So D will be selected first because D is the shortest job in the waiting queue. In the waiting queue, there are 4 jobs. D is the shortest one, so D will be executed first. And D needs 4 minutes to finish its job, so at time 4, D just exits, and then the next shortest job is C, right? And C needs 6 minutes, so it means 4 plus 6 is equal to 10, right? So 10 at time 10, C just exits, and then B, and then A. So you can see the final completion time for this for the same batch of jobs is exactly the same. They all finish all the 4 jobs at time 28, but the execution order is different. And you can see the turnaround time is different too. So here, if we need to calculate the average turnaround time for SJF, I need you to tell me the turnaround time for job D is the turnaround time for job D should be the number should be can let me see is Mohammed here number 30 Mohammed yes 0130 Mohammed, are you here? Okay, so we just choose select another one number 6. So sorry, oh, you're on. So who is this? So okay, is so here? Is so here? How about Russell? Is Russell here? Can you hear me? Okay, Russell, you are here. Good. Do you did you hear my question? I need you to give me the answer about the turnaround time of job D with SJF. Did you follow me to schedule for these 4 jobs? What's the turnaround time for job D? The turnaround time for a job is the duration between the submission time and the completion time. So you can see it very clear from this axis. Time the completion time for D is 4, and the submission time for D is 0. So the turnaround time for D should be 4 minus 0. It should be 4, right? Right? Okay, so now you just tell me the turnaround time for job C. So the turnaround time for job C is, you can check the axis, because we will have the similar questions on the assignment, both the assignment and the quiz. So all of you need to understand how to get the correct solution, get the correct result based on different algorithms. 6? No, it's not 6. 6 is the execution time. For a job C needs 6 minutes to finish its job, as the problem mentioned, but the completion time for job C is 10. Because job C has to wait for 4 minutes, because during this 4 minutes, job D is using the CPU, and at any instant, CPU can be used by only one job or one process. So the turnaround for job C is the completion time 10 minus the submission time 0. They all have the same submission time. They all arrive at the system at time 0. So the turnaround time for job C should be 10. Yes, yes, good, Grace, Chris. So I hope all of you can understand these simple steps relevant to the turnaround time, because it steps are relevant to the turnaround time, because it might cost 10 marks in the quiz, and also we have the similar questions in the assignment. So I just list the turnaround time for each job here. The execution order with SJF should be DCBA, and you just need to subtract the completion time with the same submission the same submission time. So the turnaround time for job D is 4. The turnaround time for C is 10, because 10 job C get into CPU at time 4, and it just runs 6 minutes and exits the system at time 10. But the turnaround time should be the you should get the turnaround time by subtracting 0 from the completion time. So this is the turnaround time for job C. Similarly, the turnaround time for job B is 18, and the turnaround time for job A is 28. So you can see with this exactly the same batch of jobs, for these 4 jobs, we try 2 different algorithms. FCFS, it gets the 20 minutes. The average turnaround time for FCFS is 20 minutes, but the one for SJF is only 15 minutes. So for this example, you can see SJF is better than FCFS, because for the batch systems, the shorter the turnaround is, the better the algorithm is. So this is a very simple example, because they all have, we suppose they all have the same submission time. But if we suppose they have different submission time, as showing in this example, you can see we just suppose there are 5 jobs with different run times of 5, 2, 3, 7, and 1, and their arrival times are 0, 1, 3, 4, 5. It means they just arrive at the system in at different time, right? This is the real case in the world, because it's very hard for a lot of jobs. They just arrive at the system simultaneously. Usually they just arrive at the system at different time. So for this example, we can get the result looks like this, and the how to get that result, I have to illustrate the procedure to get the final result again, because this is very important for you to grasp. You need to understand how to apply different algorithms onto a scheduling problem. So here, if you just missed something a few minutes ago, from now on, you need to follow me to grasp the whole method. Okay, so if we here we just focus on the first 2 algorithms. The first one is FCFS. So you need to decide the execution order first. It's very simple for FCFS, because ABCDE, that's their arrival order, and their execution order should be ABCDE, in the same order. Okay, so FCFS will just select with this algorithm. A will be executed first, and then B, and then C, and then D. So the key issue is about to calculate their turnaround time. And if you want to calculate the different turnaround time for different jobs, you need to know the different completion time for each job. For job A, it starts execution at time 0, and it needs 5 minutes or 5 time units to finish its job. Here, I strongly suggest you to represent the scheduling problem like this. with these circled parts, you can see it clearly. See it clearly that the A arrives at 0 and its runtime is 5. For job B, it arrives at time 1 and its runtime is 2. And for similarly for job E, it arrives at time 5 and it needs 1 unit to execute its instructions. So after you just represent the problem with this way, in this way, you can move on to the next step to schedule for this same batch of jobs with or even more different algorithms. So for FCFS, A starts execution at 0 and finishes at time 5. So at this point, we need to call the scheduler to select the next process or next job, right? And we just ignore the switching time. We just let process B or job B get into CPU immediately and run for 2 minutes because as this figure shows, B needs 2 minutes to finish its job. So it means the completion time for B should be 7, right? Right? 7. At time 7, B just finished all its job. It just runs for 2 minutes and it exits. So at this point, the CPU is available again, and the scheduler will choose the next one. It should be C, and C gets into CPU at time 7, and after 3 minutes of running, it exits at times 10. And then D gets into CPU and runs for 4 minutes and, oh, I'm sorry, runs for 7 minutes and exits at time 70. And then it's the last job. The job E gets into CPU at time 17 and exits at time 18, because E is a very short job. It just needs 1 minute. But with FCFS, it has to be to stay to the end to get the CPU, because in with FCFS, the jobs get the CPU according to their arrival order. So this is for FCFS, and here when you calculate the turnaround for each job, you need to be very careful about the submission time because they have different submission time. For the turnaround time of job A, it submits at time 0 and finish at time 5. So turnaround time for job A is 5 minus 0. It should be 5. But for the job B, you can see B arrives at system at time 1 and it finishes its job at time 7. So the turnaround time for job B should be 7 minus 1. So this is the turnaround time for job B. And the same way you can see for job C, it except its completion time is 10. So the C exits at time 10 and it arrives at system at time 3. So the turnaround time for C should be 10 minus 3. And you can get the turnaround time for job D should be 17 minus 4. 17 minus 4. And the turnaround time for job E is 18 minus 5. So after you get five different turnaround time for these five jobs respectively, you can get the the average turnaround time should be 8.8. So this is the case for FCFS. And for the same batch of five jobs, you can see if we adopt SJF, the execution order is totally different. Okay, so in this example, we just give you a simpler version about this different arrival orders. Because you can see after at the very beginning, you can't just select job E to use the CPU. Because at the very beginning, there is only one job in the system. Okay, at time zero, B, C, D, E, they haven't arrived at the system yet. So at very beginning, you need to focus on this because this is very important, and a lot of students just make mistakes here. They thought, oh, we choose SJF and the shortest job is job E, so job E should be the first job which gets the CPU, but they just forget that job E is not here yet at time zero. Job E arrives at system at time 5. Okay, so just notice this. At the time 0, there is only one ready job. So scheduler has no other option but to select job A to use CPU, and A will execute for 5 minutes. Okay, because SJF is a non-preemptive algorithm. It means only when A finishes its job and leaves and releases the CPU voluntarily, A will exit the system, or A can block itself during the execution. But for this case, we don't we just don't suppose that a case happening. Okay, we can see here we just suppose as long as a job gets CPU, it will run all the instructions and finish its job here. So for job A, it will it will exit the CPU, also exit the system at time 5, right? The same with FCFS. And at this point, you can see in the waiting queue to get into CPU, how many jobs are there at time 5. At time 5, B, C, D, and E, all of these 4 jobs, they just arrived at the system, right? So at time 5, the scheduler need to select one ready job from the 4 jobs B, C, D, E, and which one will be selected according to SJF algorithm. At time 5, which one will be selected? Is Ibrahim here? Ibrahim, are you here? Ibrahim, are you here? Okay, so let's see. How about Michael? Michael, are you here? Okay, you just tell me the next job which can get CPU after job A exit should be which job will get the CPU next after job A leaves. After job A exit, what's the next job here? We should choose one from B, C, D, E at this time. And we should, according to the idea of SJF, we need to choose the job with shortest running time, with shortest execution time. So here we should put job B here. Oh, job E, yes, I saw a lot of correct answers from you. Thank you. Some students tell me we should choose E, right? Correct, good. So because at this time, all the other four jobs arrive at the system, and among these four jobs, you can see job E has the shortest time according to the idea of SJF. So E should be the next one to get CPU, not B. B is the if B wants to get into CPU next, the algorithm should be FCFS because B has its runtime is 2 minutes. It's longer than job E. For SJF, of course, we should choose job E here, and E just needs only 1 minute to finish its job. So at time 6, E just exits system. And at this time, oh, here is another scheduling time, right? Because CPU is available again. So the next here at time 6, the next job to get into CPU should be the next shortest job, right? It should be B. Very good. Okay, so next one should be B, and B needs to run for 2 minutes and exit the system at time 8. And then C will take CPU to run for 3 minutes and exit at 11. And then the last job will get CPU for 7 minutes and exit at time 18. So you can see with SJF, we have a totally different execution order. And here we just suppose they have different arrival times. So when you calculate the turnaround for these 5 jobs, you have to be very careful. You should submit the you should subtract from the subtract the completion time by the different arrival time. For example, the turnaround time for A should be 5 minus 0, and the turnaround time for the second job exit the system for the job E, its turnaround time should be 6 minus 5. And the turnaround time for B for the next job should be 8 minus 1. It might be a little bit mess, but I just need to draw the line between the matched values. So for job B, its turnaround time is 7, and for job C, the next one, the job C, its completion time is 11, and its submission time is 3. So the turnaround time for job C is 8, and the turnaround time for job D is 14. And if you get the average value of for these 5 numbers, you can get the final result is 7. Okay, so this is different turnaround time for different algorithms. And these 2 algorithms are the most simplest, are the simpler one if you learn more algorithms later. So based on the simpler, based on these two simplest algorithms, I hope you can already grasp the way to provide the solution, provide the scheduling scheme based on the CPU axis. and then we can move on to the next algorithm, which is a little bit complicated. For this, the third algorithm we are learning is called shortest remaining time next. So here you can see it's preemptive. That for batch systems, we usually adopt non-preemptive algorithms, but there is exception. Sometimes we need to get how to say, we need to get the we want to get a better performance based on the shorter turnaround time. And usually if the jobs arrive at the system at different time, we should we can try to adopt this shortest remaining time next to get better performance compared to SJF and FCFS. If the users submit if the users who submit the job don't care about the completion time, if they don't care about the final their own completion time, and from the perspective of the whole system, which needs to handle a lot of batch jobs, they can choose this algorithm to get a better performance from the system perspective. Okay, so maybe for from the personal perspective, for a certain user, it gets worse performance with this algorithm, but sometimes we should adopt this algorithm from the system perspective. Okay, so let's just check this basic idea of the shortest remaining time next. It's a little bit complicated because you need to do more calculations. It needs to choose the process whose remaining runtime is the shortest. Remaining runtime is the shortest, which means at any point you need to run the scheduler, you need to calculate the remaining runtime for all the processes in the waiting queue, and you choose the shortest. So here, I just jump over all the explanation because we just need to, I think it's better to illustrate you how to apply this algorithm with the same, with this same scheduling problem. So here, let me just, with the same scheduling problem description, if we adopt shortest remaining time first, you can next you can check the algorithm description again. We choose every time we need to choose a process to run next. We just choose the process whose remaining runtime is the shortest. This is the basic idea of shortest remaining time next. So let's back to this axis. Here, if we need to use shortest remaining time next, at the very beginning here, at time 0, you can see we have the same question. At this point, there is only one job in the system, right? So here we don't have no other options. We have no choice but to let job A get into CPU for 1 minute. Why just only 1 minute? Because here you can see in the system the job B arrives at this system at time 1. So here is you need to call the scheduler because there is one more new job or one more new process which is in the ready state. So at this time, even though process A needs to needs to run the instructions for, oh my God, my network has some problems again. Can you hear me? Okay. So let's just continue. At this time, at time zero, even though process A needs to use CPU for I just set the wrong alarm clock. So sorry. So let's come back. Okay. At time one, even though process A needs to keep using CPU for 4 minutes, right? But at this time, there is another job which is in the ready state. So according to the basic idea of shortest remaining time next, the scheduler need to compare the remaining time from job A and B of job A and B. A needs 4 more minutes to finish its job, but the new arrived job B, it just needs 2 more minutes to finish its job. So at this point at time 1, process B or job B will just take the CPU away from job A, because process B, the remaining time for job B is 2, and the remaining time for job A is 4. Process B or job B has shorter remaining time, so process B can take CPU away from job A at time 1. And after 2 minutes, at time 3, here you can see B just finished all its job and B gets out of exit, right? Exit. So B exits at time 3, and this time you can see there is another new job arriving at the system, which is job C. And job C needs 3 minutes to finish its job, while job A, the first job which gets CPU, which still needs 4 more minutes. So C is shorter than A. We don't compare their original run time. We compare their remaining job time, remaining time, run time. Okay. So at this point, you can see C will take CPU away and run for only 1 minute. Why C can run only 1 minute? Because at time 4, there is a new job arriving at system again. But you can see here the new arrived job D, it needs 7 minutes to finish its job. So among A, C, and D, here A needs 2 more minutes at time 4. At time 4, A needs 4 more minutes, C needs 2 more minutes, and D, the new arrived job D, it needs 7 more minutes. So at time 4, the scheduler will run for a while to decide which job can use CPU next, and it just selects C. It still selects C, but C just at this time you need to understand C cannot keep using CPU at time 4. C just compete for the CPU along with job A and D. C can stay in CPU only because C has the shortest remaining runtime. Okay, so here scheduler is called again at time 4 and decide to let C continue using CPU. And then at time 5, here you can see E is coming. E is coming while E has, E has only 1 minute to run, right? E only needs 1 minute. But at time 5, you can see C process C or job C, it just runs 2 minutes. And also C needs only 1 more minute. So here you can choose different, you can make different choose and let's maybe the new one to start to use CPU or just let C continue to finish its job. It's up to the operating system, but here you can see we have different final turnaround time, average turnaround time if we adopt shortest remaining time. And this is obviously this number, this average turnaround time based on shortest remaining time is much less than the FCFS and SJF, right? And I just list the possible execution order for these 5 jobs. You can check it. You can try to get this answer after the class. But by the way, I have to say I don't need you to apply this complicated algorithm to solve a concrete scheduling problem. Usually, you just need to master some simple algorithms such as SJF, FCFS as non-preemptive algorithms, and round-robin scheduling algorithm and priority scheduling algorithm. You just need to master how to apply this for simple algorithms to schedule for some jobs. It's enough. For the other more complicated algorithms, you just need to understand their basic ideas. You don't need to solve a concrete scheduling problem based on them. Okay, so we just discussed the two simple algorithms for batch systems, which are non-preemptive. And from this slide, we're gonna learn some preemptive algorithms for interactive system. So the first one is very popular in the modern operating system. Also, maybe you can see some modified version based on this round-robin scheduling. Its basic idea is to allocate each process in the system with a fixed slot, a fixed time slot, and we call it a quantum. So each process can get a quantum when it gets the CPU. It can use the each process can get into CPU and run for a quantum, and then it has to get out of the CPU to let the next process in the waiting queue to run the next quantum. So you can see this round-robin scheduling, it sounds very fair for all the processes in the system, right? So each one they just take turns to use CPU for a fixed time slot for the same time, and this same time interval is called quantum. So, but you can see for this algorithm, uh, you need to uh, design the length of the quantum very carefully, because the different length of the quantum will just brings different performance for the whole system. You need to carefully decide the length of the quantum, 1 millisecond or 10 milliseconds or 100 milliseconds. How long can a process get use CPU? So you need to decide the length of the quantum for this round-robin scheduling algorithm. You can see the basic idea from these figures more clearly. So in figure A, it's the list of runnable processes. It means the waiting queue for the CPU, the queue of the processes which are waiting for the CPU. So in this list, you can see B, we suppose process B is the current process, and then F should be the next process which gets CPU. And after F leaves CPU, D will be the next one to get into CPU, and then G, and then A, and again B can get CPU back. So everyone just takes turn. Everyone takes turn to use CPU for the same time, for the same quantum. So after B gets out of CPU, it will just be put. It will be put on the at the end of the queue, and then FDGAB, FDGAB cycle. Okay, so this is the basic idea of the round-robin scheduling. You can see it more clearly from this figure. And as I said, the length of the quantum is very important for the performance of this algorithm. So let's see if the length is too short or is too long, what happens to the whole system? As we know, as I mentioned before, actually between the two processes switch, I mean, when the current process needs to get out of the CPU and before the next process gets into the CPU, actually there is a time interval, right? During this time, we need to run the scheduler to select the next process. We need to give the CPU some time to store the information for the current process and get ready for the execution of the next process, right? So usually we just ignore this time interval between the last process getting out of CPU and the next process get into the CPU. But actually, this time slot does exist, right? So here, if we suppose we need 1 millisecond to switch process to switch between the last process and the next process, and each process, as long as it gets CPU to run for a while, we suppose the quantum is set as 4 milliseconds. So it means every 4 milliseconds you need to spend 1 millisecond to switch between the last process to the next process. That means you just pay 20% overhead for each process for the whole system, because every 5 milliseconds, only 4 milliseconds are used to running some instructions from the application processes, and the other 1 millisecond is used for the switching operations, right? So the overhead for this quantum setting is 20%. If we suppose we need to take 1 millisecond to finish some process switch jobs, then the overhead is 20%. But if we just set the quantum as a long number, as a big number, if we set a quantum as 100 milliseconds, That means every 101 milliseconds, you just need to waste 1 millisecond to handle those issues relevant to process switch. And you can use 100 milliseconds to run some real instructions relevant to the application processes, right? So you can see if we set the quantum as a big number, we can get much lower overhead. We don't waste a lot of CPU time on the process switch. But this causes another problem because it means everybody just staying in that waiting queue to wait for the CPU. And if the quantum is very long, then the last process in the queue has to wait for a long time, a much longer time, right? And we see round robin scheduling is a preemptive algorithm. It's used in interactive system. So if we set the quantum as a much bigger number, then it means the users who just send their request into the system, maybe they need to wait for over 1 second or 2 seconds or even longer to get their request to get their response for their to their requests, right? So it's not acceptable for the common users to wait for such a long time. So we cannot, even though the longer the quantum is, the better the lower overhead is, but we cannot set the quantum as a much bigger number. We can't set the quantum as long as possible because if it's too long, it causes the time for it causes the problem for the user experience. And we cannot also set the quantum as a smaller, as a much smaller number, because you can see if it's too short, it just causes too many process switches and the overhead is very high. And it means you just waste a lot of time on the meaningless operations, because only the instructions from the application processes are doing something meaningful behaviors. The other the other instructions, the other operations on the process switches, they just from the management behavior. They just for the management behavior. They don't create any values, right? So it means we can't set the length of the quantum too short, and also we can't set the length of the quantum too long. So what's the what's the suitable length for a quantum based on the experiments and lots of user experience investigations? We can set a quantum around 20 to 50 milliseconds. So you can just understand there is a suitable length of a quantum. We need to set the reasonable length for a quantum. It cannot be the quantum cannot be too long or cannot be neither cannot okay, so the quantum is neither too long nor too short, and 20 to 50 milliseconds is usually a reasonable compromise. So this is the one more thing you need to know about the round robin scheduling. But generally speaking, the basic idea for the round robin is much simple, right? You can just list all the processes in the list in a waiting queue and let them take turns to use CPU for a fixed time for one quantum. Every process gets into CPU and runs for one quantum, and then the clock interruption will just remind the scheduler to run for a while and select the next process to get into CPU for to run for another quantum. Every process gets into CPU for one quantum and leaves CPU and waiting for the next round. So this is called round robin scheduling. And while you are doing the homework, while you are doing the assignments at the end of this PowerPoint, you can check. We just set a problem about the round robin scheduling, and maybe it better for you to just put them in the time axis relevant to the CPU, just as I showed a few minutes ago. So this is about round robin scheduling, and the last algorithm you need to master is the priority scheduling. So this is the basic idea for this algorithm is just to select the every time when the scheduler is running, it just selects the highest priority. So this is very simple too, right? Just like the SJF, you just need to select the shortest job. And here you just need to select the highest, the job, the process with the highest priority. So you can see how to set the priority is very important. Which process can get higher priority and which nobody wants to get lower priority, right? So in the next class, then we'll talk about something to dynamically set the priority or use the quantum. Use this quantum to solve some issues caused by the original priority scheduling. So that's all for today, and we're gonna take the lesson. Yes, next Wednesday. Okay, see you next Wednesday. That's all for today.